Hello YouTube, welcome to part 7 in my video series on classical mechanics. If you're watching this video, there's a good chance that you were already familiar with the material I've covered in my last 6 videos, and you just fast forwarded through them, just to hear about gauge theory. Okay, but in any case, to recap, we started off by discussing dynamic optimization and the Euler-Lagrange equation. These equations are the basic ingredient for understanding the least action principle of classical mechanics, also known as the Lagrangian formulation. I discussed Noether's first theorem, which connects symmetries of the Lagrangian with conserved quantities. Then I translated these results into the Hamiltonian picture by a Legendre transformation, which is a coordinate transformation from velocities to momenta. Within the Hamiltonian formulation, canonical transformations are special coordinate transformations that preserve Poisson brackets and allow us to formulate the Noether theorem in the Hamiltonian language. One special time-dependent canonical transformation removes all time evolution from the system and therefore replaces the need to solve the Hamiltonian equations with a single first-order nonlinear partial differential equation called the Hamilton-Jacobi equation. All of these results assume we can invert the Hessian matrix, Wij, in the matrix expression of Euler-Lagrange equations. But what happens if we can't? Gauge theory is my penultimate topic in this video series, and for some people it's a scary topic that they try to avoid. There's no good reason to be scared of classical gauge theory. Quantum mechanical gauge theories have tricky issues with normalization, but that's another story for another day. Okay, so suppose we have a system with a singular Hessian matrix. For every missing rank, or co-rank, there exists some linear combination of rows that add to 0. If we combine the Euler-Lagrange equations in these multiples, we cancel out the acceleration terms to produce a relationship between first-order derivatives called a Lagrangian constraint. The null space vector that kills the acceleration, we're going to call that gamma. In the Lagrangian picture, we still have n independent equations for n unknown functions, except some of them are first order and some of them, called Lagrangian constraints, are first order. Okay. Let's see what is actually happening in the Hamiltonian picture. We need the velocities in terms of momenta, but the Jacobian of the transformation is the Hessian of the Lagrangian, which is singular. A singular or degenerate transformation would compress these n velocity coordinates onto some submanifold of momentum space called the primary manifold. Each point represents an entire family of possible velocities. We could take any velocity vector and add an infinitesimal multiple of gamma, the null space vector, without changing q. And this won't change p either. Alright, let's check. What's the change in p defined as dl dq dot? Well, it's dp dq dot times a change in q dot. The Hessian times gamma equals 0, by definition of gamma. How do the p's and q's evolve with time? Well, in the regular case, q dot as a function of q and p tell us how q evolves, while Euler-Lagrange tells us p evolves as dl dq, which depends on q dot, and t. But in the singular case, this inversion takes us to some arbitrary point on the family of velocities. This one evolution vector lies on a whole family of equally legitimate possibilities. The possible velocity vectors all differ by multiples of gamma, while p dot correspondingly differ by this mixed partial times gamma. It looks like Euler-Lagrange is indifferent between all these possibilities, but this freedom is deceptive because singular systems are constrained to stay on the primary manifold, whereas in the regular case, phase space coordinates are physically meaningful everywhere. There are 2 n dimensions in phase space, but the primary manifold loses a dimension for every rank missing from the Hessian, while the space of possible evolution vectors starts at 0 and gains 1 for every missing rank. So these two surfaces intersect in 2n-dimensional space at a single point. So this schematic here represents the primary manifold as some 2D surface and the space of possible evolution vectors, let's say that's some 1D line intersecting in 3D space at a single point. Now the problem here is to find the point of intersection. How do we pick out the evolution vector, this arrow here, that actually lies inside the primary manifold? We can represent the primary manifold using constraints phi equals 0. Because phi is constant, its directional derivative along the physical manifold, this dot product, vanishes. The gradient vector is perpendicular to the manifold, and there is one linearly independent constraint for every dimension missing from the primary manifold. Together with one linearly independent vector for every dimension in the manifold, we have a complete orthogonal basis of vectors in phase space. To lie in the primary manifold implies that it represents some physical change in position. Let's say x and or changes in velocity, y. Let's represent the delta vector in a slightly different basis, where we swap the q and p components and put a minus sign there. That doesn't affect the property that we still have an orthonormal basis. Now, if all dot products were orthogonal in the old basis, they're also going to be orthogonal in the new basis. So to find k, let's dot both sides with one of these tangent vectors, ti. The right-hand side becomes ki, while these two terms on the left cancel, while this term vanishes by the definition of gamma. So that leaves a convenient expression for all possible evolution vectors, k equals 0. We now solve for lambda so that the evolution vector will stay inside the manifold. This means that we want the time derivative of each constraint, phi, to vanish. The time derivative of one of these constraints depends on its change with the q and p coordinates, which becomes the Poisson bracket with the Hamiltonian plus all the constraints. So we need to solve this system of linear equations. If this matrix of Poisson brackets is invertible, then we're done. But if it's singular, we can perform Gaussian row reduction operations and redefine these constraints to produce some linear combination, let's call it chi, whose Poisson bracket with everybody else equals 0. Chi has to equal 0 and stay 0, but in some places on the primary manifold, it can never happen. Okay? Since lambda has no bearing on chi dot, this means we only look at the part of the manifold where the bracket between chi and h equals 0. And in some sense, this function chi dash is a new constraint, a secondary constraint. And if we want to stay on the manifold where chi dash still holds, then we have a new condition which says that the Poisson bracket between chi dash and the Hamiltonian vanishes. We replace our row of zeros with the Poisson brackets between chi and the original primary constraints. But what if this matrix is also singular? We once again form a row of zeros and look at a new constraint, chi triple dash equals the Poisson bracket between chi double dash and the Hamiltonian. Okay, so all these constraints remind us that some points on the original manifold are physically inaccessible. The part of the primary manifold that also satisfies the secondary and tertiary and quaternary constraints, that satisfies all the constraints, is called the physical manifold. Okay, let's do an example. Consider this fixed rotor. Okay, so if you add this term to the Lagrangian of a free particle, you get the behavior of a particle constrained to move along a circular locus. This k is a dynamical variable with a velocity and momentum, and these are the Lagrangian equations of motion. If you want to convert to the Hamiltonian picture, the Jacobian of the transformation is singular, so all possible position and velocity combinations live on the primary manifold, where the constraint phi equals pk equals 0. To find the Hamiltonian, we arbitrarily choose one of the many possible inversions and substitute to complete the Legendre transformation. These Hamiltonian equations give one possible instantaneous evolution away from one point on phase space, but any choice of lambda is equally valid, so we want to strategically pick one lambda that will keep pk equal to 0. And we can see here that the Poisson bracket has nothing to do with lambda. This phi doesn't generate a consistency condition for lambda, rather it produces a new constraint. Chi dash equals x squared plus y squared minus r squared. Okay, but what is chi prime? Does it generate a consistency equation? No. The evolution of this quantity, chi double prime, has nothing to do with lambda either. So we have yet another constraint. Does the evolution of chi double dash have anything to do with lambda? No. The bracket gives another constraint, chi triple dash. But this one looks more promising because k has a non-zero Poisson bracket with pk. So the evolution of chi triple dash does depend on lambda, and this is the consistency equation that we seek, because by picking the right lambda we can make chi triple dash stay equal to 0. If chi triple dash starts as 0 and stays as 0, this guarantees that chi double dash does likewise, and same for chi dash, and finally phi. Our original constraint stays 0. So there you have it. Here are the equations of evolution. It's simpler than it looks because we're only interested in the physical manifold, the points in the four-dimensional phase space that satisfy all the constraints we found. In particular, k dot and pk dot both equal 0 because these are constraints. So k is just a constant number, and these equations tell us that the particle traces out a circle at a constant velocity. So this is an example of a Lagrangian system with a singular Hessian matrix, but it has a single defined path. If you know the position of velocity at the beginning of time, you know its future position and velocity and acceleration and everything else until the end of time. And that is not a gauge theory. In my next video we will look at a different type of singular Lagrangian that does produce a gauge theory.